Morning, DiffCVML participants. Welcome to my talk. I'm Pavan Turaga from Arizona State University, and I will be talking about invariants and the role of geometry in it. The talk is titled Revisiting Invariants with Geometry and Deep Learning. And this is joint work with my ex-students, Suhas Lohit, who is now at Mitsubishi Labs, Boston, and Chao Wang, who is now with SRI Princeton. The theme of this talk, so I'm trying my best to work with, oh, okay, Zoom recordings. I apologize for any hiccups along the way. And of course, I'm available outside the talk via email for questions. All right, so now I figured out what to do. All right, so invariance in computer vision is a very old topic, which has been visited again on and off with different kinds of tools. And back in, the early days of computer vision and machine learning, invariances were thought of as ways to get robustness or being insensitive to certain factors of variation, like the viewpoint of a camera, blur, changes in illumination, movement, so on and so forth. And for each of these different factors of variation, people were able to come up with some limited kinds of invariants. And more often than not, it was almost impossible to find true invariants in any situation of real interest. And then the idea of invariances became slightly weaker as the years progressed. And by the time I came to grad school in the 2000s, people started talking of invariants as a surrogate for the idea of robust descriptors, which is you want to have a descriptor of a scene, of a picture, a video, a clip of time series, what have you, such that it is robust to some perturbations or some other physical variables that might affect it. The idea of achieving true invariance was not considered a fruitful area of inquiry. And then of course deep learning happened in 2012 in that area, where the idea of invariance was, or even robust descriptors, was somehow sublimated to this idea of learning representations through data without necessarily paying too much attention to the phenomena that affects the data. In other words, the dominant philosophy for the last almost 8-10 years has been, if you're interested in classification problems, if you're interested in a specific end goal, let the data tell you what the representation is that works best for the goal. And let's not worry too much about very precise things like invariances or even robustness. And if you need it to be robust, just feed in more data with the variations that you want to be robust to. However, before I proceed a little further, let's talk of a few simple problems in computer vision where the idea of invariances has still not been fully solved despite all these different themes. As viewpoint variations are one of the classic, right? If you have a 3D object and you're looking at it from different views, some things are going in and out of the view. There is no simple transformation that can explain how viewpoint variations create new pictures when the object under study is a fully 3D object and not just a simple planar patch or even simple collections of simple planes. When you have complicated objects with convexities, concavities, there's all interesting things that happen, including self-shading occlusions, which are hard to model. And even with the recent advances in deep learning, there is still this unsolved problem. How do you get a descriptor that is invariant to viewpoint? Still open. Illumination is another classic. Objects and the way they look to the eye or how their intensities are recorded on a camera is a significant function, is a very nonlinear function of many variables, including, of course, the angle at which you're seeing, the reflectance properties of the object. Most of the objects in this picture that you're seeing seem to be what are referred to as Lambertian objects, meaning they don't necessarily have any glossiness. They are matte, or in other words, when you write down the equation for reflectance, a single ray of light falling on a single point reflects off roughly equally in all directions. There is no preferred direction of reflection like a mirror. But what if there are mirrors? And what if, and most practical objects of interest do have some glossiness. They do have some metallic, features, which are not easy to model. So even under this restricted assumption of Lambertian reflectance, it's been very hard to model, because then there are other variables like the geometry of the object, self-shading and reflections and other kinds of occlusions are also present even under these restricted assumptions. Then of course there is movement, another classic problem, which is many objects that you are interested to represent and to recognize have certain degrees of freedom, which allow them to deform. Things like human bodies, things like animals, even objects like tanks and cars, which you might think of as rigid objects by and large, but they still have moving parts. You can open certain doors, windows can go up and down, and any of these little things can change how the picture looks. And it's a classic problem in the defense industry. If you have a tank with a turret, and depending upon how the turret is spinning around, the signatures of the tank can look very different in different imaging modalities. So this idea that movement is a variable is also a very difficult thing to contend with, because there are no simple equations you can write that describe the movements of these non-rigid objects. And of course, there is this completely, this is semantic variation, which I'm talking about here, which is given a single object class, what is a chair, irrespective of illumination, viewpoint, deformations, there is this entire higher level of variability, which may best be called semantic variability, which is, yeah, I don't quite know, I can't define a chair in a simple, concise way. And human creativity is amazing. Many different objects can arguably be called chairs, and it's just not easy to model it with an equation. So that we are not even going that far. That is semantic variability, and probably data-driven methods are best at this stage. But for some of the other kinds of variability where we do have some idea of the physics of image formation, we may be able to do something better than just relying on data, and that's what is this talk about. As I was talking earlier, before the advent of deep learning, invariances were talked about in a couple different ways. One is for very specific factors of variation, you could write down some very special equations. Assuming we are talking of imaging objects under movement, one of the ways in which a whole body of work emerged was to think of a CAD model of an object, and that applied to things like vehicles, tanks, where you could assume that there are a few rigid parts which are connected by some mobile joints. So you could have a CAD model that describes the object with certain degrees of freedom for each part. And then the group of rotations would be that variable which represents the viewpoint of the camera, which you're trying to factor out. And you could do some interesting forward models, and you could do some interesting optimization problems where the optimization variable, either you would optimize out over this unknown pose, or you would integrate this observation model over all poses. So either you marginalize it out or you minimize certain cost functions over this variable. And that led to a whole body of work, and many of the senior faculty here in DiffCV have done work like this, including Anuj, including Baba, including Tamal. I'm sure many people have done stuff like this. With deep learning, the topic of invariance has shifted. And of course, before this, there was this intermediate phase where the idea of invariance just became a different word for robustness. So things like SIFT, scale invariant feature transform, very famous image or patch level descriptor, which is quote unquote invariant to scale, but it's not truly invariant to scale. It is only robust to a few scales, but it was named such, scale invariant feature transform, with the full understanding that it's not truly invariant. And then there was a phase where the word invariance just became robustness. With deep learning, this discussion somehow went away, and the idea was, let's just let the data figure this out. Whatever the representation is, whatever it tells you, has to be the right one, given enough data. And this is a paper from 2009. Still, some of the conclusions from this paper are still relevant. This is called Measuring Invariances in Deep Networks, where the authors, and Andrew Ng is, of course, very famous. Ian Goodfellow is very famous too. Many famous authors now. they probed a few standard deep networks with very carefully constructed probe sets. So you would take AlexNet, this classic image classification network, and probe its invariant properties by taking a picture and let's say you keep rotating it very carefully. And then you keep tracking the activations along the neural net to see if there are some neurons which are, of course, equivariant maybe. And if there are some neurons which don't change at all, those would be the invariant neurons. And what happens? How many are there and where are they? And they made some interesting findings, which is this idea of invariances. This idea of invariance is very hard to actually get reliably. There seems to be no easy answer to get a set of invariant neurons to any specific factor. And this conventional wisdom that make the networks deeper and deeper and deeper seem to have only modest improvements beyond a point. It just did not work after that. And they did mention towards the end that there are some simple factors which you can be invariant to, like these max pooling operations that are popular in neural nets give you some amount of small shift invariance in pictures. But to get more intricate invariances like viewpoint transformations to rotations, large out of plane rotations, complex illumination changes is unsolved. And it is still very much true. Nothing much has changed since then. On the empirical side, this is a nice picture I like from one of my own colleagues from Arizona State. They went in to probe, again, the invariant properties of certain standard nets. And the way they were probing it was by inducing artificial degradation transforms on pictures. So these are some standard networks: VGG16, GoogleNet, VGG-CNNS, Cafe Reference. These are standard image classification networks. And this shows how their performance drops on classification under simple things like Gaussian blur with certain standard deviation. And as the standard deviation increases, how the performance drops, noise, and contrast level. So almost every physical factor that you can actually simulate will cause these things to drop very dramatically very soon. So we are interested in a middle ground, which is try to come up with, it's not, but there is something to be said about the success of deep learning, which is the features that it learns seem to generalize well under stable operational conditions. Sure, if you have not trained it on certain viewpoints, it will not generalize. But as long as you've trained it on certain viewpoints, certain intermediate viewpoints, even if they're not observed, your deep neural network does a good job of interpolating, even though it may not be as good at extrapolating across views. So it may not have that invariant property, but it seems to do well in interpolation kind of problems where some of these intermediate things can be filled in by the neural net. So it's not very productive at this time to say, let's reinvent the wheel. We have to take the successes that deep learning offers and try and find ways in which we can bolster their performance with the knowledge that we have from the older models of the physics of image formation, group theoretic ways of thinking about invariance, and other geometric ways of thinking about invariance. We will talk of two models in this talk where we have been able to achieve some success, and I shall end with some directions that we are taking. The big theme is, it's preaching to the choir in this group, but anytime there is this idea of invariance written up formally, it somehow becomes a geometric problem. And the intuition is not hard to see. You have features living in some big ambient space, Rn, and by invariance, we are basically identifying certain equivalences. We are saying this feature in this location, that feature in that location, refer to the same thing. And the fact that they are far away is simply because of some physical nuisance factor. So we are trying to take this ambient vector space of features and then trying to paste them together based off of some identified notions of similarities and equivalences. And if that act of pasting is nice and it follows certain rules, what happens is the space gets crumpled up into a slightly nicer structure. And if you're lucky, it will have the structure of a manifold. If you're not lucky, there's nothing you can do about it. But in some cases, under certain restricted assumption, this act of taking this ambient feature space and imposing these equivalences through physics leads to certain, under weak conditions, some nice spaces. So we shall see some of those examples. The first example we will look at is this idea of rate invariance in activity recognition, where you're looking at activity as a time series, which is evolving in certain feature spaces. And that feature space can be from a simple scalar valued accelerometer based sensing of human movement. It can be a stick figure which has been sensed from a motion capture system or a depth camera, or it can even be a video frame which has been, where a human has been detected and tracked over time. So the features you're looking at are computed from the picture. We think of human activities as these time series evolving in some feature space. There has been work also in actually asking what is that feature space. And if you go deep, yes, you can think of it as shape sequences and you get sequences evolving on manifolds, but we are not going that far. We are saying the feature that we have is plain embedded in some vector space in Rn. We are not being too specific about features for a reason, because if we get too specific about features, we are limited in what kind of features we can talk about. For special things like stick figures and silhouettes, yes, we do have some very special ways. We talk about shapes, but then it doesn't generalize to simple video features, doesn't generalize to wearable signals. So we are taking a step back. We're not telling you what is the feature, and we will let the deep learning architecture tell us, learn a feature. But we are interested in imposing an invariance on the time axis, which is how do you get invariance to stretchings of the time axis in a way that is that gives you some robustness to temporal warps of the activity. Now, this problem of temporal alignment on itself, by itself, given a very specific feature, given I give you a time series in some feature space, how do you align two sequences such that the peaks and the valleys align? That's the core problem. And that is arguably a solved problem. Classically in the 80s, dynamic time warping has done it for us. And in recent years, some of the issues in dynamic time warping were addressed by Anuj's group, including the square root velocity representations, which take care of some things like the pinching effects that happen in DTW. So arguably a solved problem. However, all these methods require that you have a feature to begin with. You have chosen a representation for every time instant. But then with deep learning, that's where the question is, what is that feature? And we do not want to marry ourselves to any feature, but yet have this idea of rate invariant somehow constrain the deep net when it learns its features. That's where we are trying to be. As a quick overview of how the time alignment problem is posed, this is again very standard language, nothing that we invented. You think of, assuming you have a feature, you think of the activity evolving in feature space. Alpha of t is the representation, t goes from 0 to 1. We want to be invariant to resampling of the time axis, which is given by this nuisance parameter gamma, which is an element of the group of order preserving diffeomorphisms, and they have a structure. It goes from gamma 0 equals 0 to gamma 1 equals 1, always increasing. And there is this time ordering property. It's always, you can't go back in time. And there are very nice representations of this gamma, including the SRVF, where you take a derivative and you interpret that function as a PDF, and then you take a square root, it becomes a point on a sphere. So we're going to use some of those ideas. And these are some properties of warp functions. In the interest of time, I will skip it. So our goal is, if your goal is classification and you haven't yet chosen a feature vector, and you're going to let a deep neural network learn a feature vector, but then also learn it in a way that is factoring out this gamma problem internal to the neural net without us having to do it external to the neural net. How shall we do that? There is some work like this, which we looked at and we took our motivation from it. This is called the Spatial Transformer Network by Andrew Zuckerman's group. Again, it's become a very, very well-cited paper in the past. Their idea was similar, which is, the question was similar. If you have a bunch of pictures and you want to learn a template in a way, or if you want to learn some features from pictures in a way, such that you have factored out affine transforms, okay? But how? Without a template, how are you transforming, how are you factoring out affine transforms? Their idea was, let's drop in a module, which is called a spatial transformer, which basically does alignment internal to this, but in a way that a template is not specified. It sort of guesses at an alignment such that the end goal of classification is maximized. And then you let the whole network run end to end, let this alignment network learn whatever alignment it learns. But the goal is not perfect alignment. The goal is maximize the end task, which in this case is classification. Learn whatever alignment you want to learn. I don't care how there is no template provided, and then maximize the classification accuracy. And surprisingly, that approach worked fine. And it is learning, this network is learning to find an alignment, which is clearly a local minima. There is no reason why it should learn meaningful alignments. But that is the magic of neural nets. They don't seem to fall into pathological solutions. They do not seem to fall into these degenerate solutions. You can always say, well, maybe the alignment is just identity. It didn't learn anything, is a possibility. But in practice, it doesn't seem to happen that way. And these are some of the mysteries of deep learning, which are not yet known, why these local minimas that it converges to still seem to do commonsensical things. So here is an example in the bottom. So these are some inputs on the left, and on the third column here are the aligned pictures without a template. So these things have been aligned to this, have been sort of normalized to these versions, all by end-to-end training with the end goal of just maximizing classification accuracy. So we were looking at some of these ideas, and we wanted to do something like this for time series. And our approach was this. Yes, we will have a module, and all that module will do is, given a time series, it will try to impose a warping function. And the warping function is constrained to be a valid warping function. And we don't quite tell it to choose a warping function. This is sort of learned end-to-end with the goal of classification accuracy being maximized. We say learn some warping as long as it's a valid warp function, meaning it has to be order preserving diffeomorphism. And that's the only constraints we throw into one of these latent layers. And we say, I'll give you time series with class labels. And within each class, there will be some warps of, there will be some hidden unknown class template. And then there will be some noise attached to it. There will be some convolutional nuisance parameter attached to it, but we will not tell you what that hidden template is. But we'll give you multiple classes with corresponding labels. Learn end-to-end some way of normalizing a given input, even a single input, such that maximize the accuracy of classification. And the key part is right there in this blue box, where there is some feature extraction happening. Now these are trainable feature extraction layers. So we are not even choosing what features to extract from the time series. That is learned end to end. All we do is have a warping module, which is physically a warp function. And then the outcome is a label. So maximize the label accuracy. And surprisingly, this does interestingly well for finding an unwarping, finding a transformation of a given time series to something interpretable. And this is how it does. So in this picture, as you see, this is just two separate classes where the peaks are slightly shifted. And then there's a lot of noise, and then there's lots of warps which have been thrown in. And our eventual network, whenever it converges, it learns to apply a different warp for each class. And here is how it looks. So class one is, whenever it sees an input from class one, it learns to rewarp it and transform it into some other form. Whenever it sees an input from the other class, it learns to rewarp it and make it look like this. So the peaks are now well separated, and it's learned a discriminative warp. It's almost like, I like to call this the Fisher's linear discriminant version of time warping. It has learned to apply a discriminative warp given a time series such that classification accuracy is maximized. Why it's done it, how it's done it is not clear, but it's very robustly working that way. A few more specific details, what is going on in the constraint satisfaction layer. It's taking an arbitrary vector and warping it into a time warp function using some standard techniques. And most of these normalization steps, these constraints that we're adding are differentiable. So they can be trained end to end with standard neural network optimization methods. This is going in a little more detail about the time warping problem. So again, data from two classes, one is M-shaped, one is bell-shaped. We synthetically add a lot of noise, additive noise, and then we also add a lot of convolutional noise to create some variance within each class. And then the TTN outputs a different set of classes, a different set of signals, which tend to maximally look different from each other. And here are the predicted warp functions. The blues and the reds are the warp functions that the TTN learns to apply to each of these classes. And on an average, here are the warps in the bottom right corner. The red and the blue are the two different warp functions that the TTN learns to apply to these two classes on an average, and they look really different. And this is learned end to end. We're not telling anything more other than just a class label. Does it actually work on real data? And then we have more synthetic results like this. We're running out of time. So I want to spend a little bit of time talking about the examples in real data sets that we have applied this to. Of course, the first application for time series and time warping is an activity recognition. And we have been doing this in different ways for many years. So we revisited that problem. We are looking at motion capture data acquired from either a full-blown rig like this or a Kinect sensor. And the representation is you have a stick figure, which you can think of in many different ways, all on its own. You can think of a stick figure itself as a graph, right? And then think of the time varying signal as some signal on a graph. Or you can think of these set of points as a shape and apply shape representations to it and think of the activity as a time series on a shape space, many things. So we are not going down that path. We are going to take this simply as a multi-dimensional time series, just stacked together. So head, neck, hand, right leg, right, whatever. It's just a time series for us without any special constraints attached. And all of that goes straight in to a deep net so that it can learn the representation that makes sense, with the only added constraint that learn it in a way that is such that for each class, you're warping out, you have learned to rewarp the input time series in a way that is discriminative. Does it work? So we have a few data sets and we find that it does work. The beauty of our approach is because we have not made a choice of a feature vector and our module of this constraint satisfaction stuff is standalone, it can be dropped in. It can be plugged into almost any neural network as long as it's optimized by gradient descent, really. It can be plugged in, no problem at all. And we have tried that on a few different standard architectures, including LSTMs, TCNs, and all these things are written up like this. So two-layer LSTM is its own thing. LSTM is the long short-term memory network. It does something, and then you add a TTN module, you drop it in, numbers bump up. So we have several architectures like this, TCN 16, but then you drop in a TTN layer, numbers go up, 64, again, numbers go up. So we are consistently seeing that when we add our TTN module, we drop it in at the right spot, of course, numbers do go up, and this is across architectures. So this is a very interesting result for us. We have done similar things for some other data sets and we found similar results. You add in TTN to a strong baseline, numbers do go up. And of course, we are able to also interpret what it's trying to do. It's not as blind as just relying on a deep net. We are imposing some structure to the deep net with some understanding of the basic phenomena. We have a few more, it's getting to be time. I will skip this. I'll mention very briefly some older work we did in illumination invariants for face recognition, and I'm going to wrap up real quick. So the other kind of invariance that we have been looking at is the idea of illumination invariance. And as I mentioned a little earlier, it's very hard to explain the effect of light on an object without knowing things like the geometry of that object and also knowing the reflectance properties of the object, the reflectance, the refractance. All sorts of optical phenomena have to be understood before we can say how does an object look under a different illumination condition. There is one body of work which came out in the 90s due to Belhumer and Kriegman and David Jacobs, and they made a few simplifying assumptions which have provided a basis for a lot of follow-on work. The simplifying assumptions were, let's assume that the object is convex. And of course, what you're seeing here is a face. A face is not convex, but it's close to being convex. Make that assumption that it's convex, and make the assumption that the object is Lambertian. It doesn't have any mirror reflectances, doesn't have too many, specular highlights. And under those conditions, they prove that under all possible illumination conditions, the set of objects that will reside on a convex cone in image space. From that convex cone result, people have developed subspace models. If you relax the convexity, given 2 points, x1 and x2, the convex combination is alpha x1 plus 1 minus alpha x2, where alpha is restricted to be between 0, 1. That's the convex combination of 2 points. If you relax it a little bit, you say, well, I'm going to allow all linear combinations. So alpha can be any real number. Then suddenly you're in the realm of linear subspaces. It's a relaxation of their classic result, but then it leads to some nicer mathematics later on. We can identify the illumination variances as a subspace, and then you can fit subspaces in any number of ways given a picture and many different illumination conditions. But a subspace gives us a very interesting way to think of illumination invariants. We are framing this problem as one of identifying the true illumination invariant by thinking of the latent invariant as a point on a Grassmannian manifold. So given a single picture, we want to find that subspace which corresponds to the illumination subspace for that subject. You cannot do it, impossible problem in the classical world. You cannot go from a single picture to a subspace without additional knowledge. So the additional knowledge we assume is we have a training set where we have observed each picture under many different illumination conditions, and we have created a training set where for all these illumination variables, we have associated this subspace, which is invariant to these illumination variations. And then given a single picture, we train a neural net to learn that subspace. I will run through this very fast. There is a few different ways in which you can parameterize the Grassmannian. The first question is, okay, it's an interesting way to think of learning a subspace from a point, from a single picture, but how do you parameterize the subspace? You can think of it as, we experimented with a few standard ones, which is, you can think of it as a projection matrix, a big square projection matrix. The obvious problem is too many parameters. And then, of course, there are fewer intrinsic parameters which you can constrain. And that's how we get there. We go down to this idea that let's look at tangent spaces on the Grassmannian, learn to regress to the tangents, which are the intrinsic coordinates. And then there's a few other details. Tangent computed at what point? Should it be at the mean point of the data set? So I'm happy to point to you a paper we wrote on this, but high level picture is, no matter how you choose these little details, we do significantly better than not assuming the Grassmannian structure for the illumination invariants. Here is a simple example. Input picture in some illumination condition. These are the ground truth subspace basis vectors for that illumination invariant. The baseline network assumes no structure on no Grassmannian structure. It just assumes that you're trying to regress a single picture to 5 other pictures, where these 5 other basis vectors are interpreted as just random pictures. And it does something, but then it loses a lot of structure. When you start imposing the Grassmannian constraint on the output, our visual quality of the results clearly goes up. So does our numeric quality of, so DG represents the geodesic distance in the Grassmannian to the true illumination subspace. That is also better. We haven't yet done a full large-scale experiment on whether this is useful in practice for a real data set, because partly because we need a way to train our network to learn to regress a single picture to an illumination subspace. So we need a training set with lots of illumination variations observed. And there's not very many data sets like that. So under some restricted data sets, like the one we just showed you, we were able to show that, yes, it does improve significantly if you were to learn the invariant and then do a recognition experiment with the invariant representation rather than the ambient representation. So that's a big jump, but then we have not yet been able to find a good way to fuse it in contemporary face recognition pipelines, where we are looking for ways to do that, but not yet. So I will conclude, I'm at the end of my talk. The big picture idea that we were talking about is to revisit the idea of invariances in computer vision by finding some middle ground between what deep learning has been able to do and what the classical methods in geometry have been able to achieve by trying to be a little flexible in not choosing a feature upfront, not choosing a representation upfront, let the deep neural network do that, but then to constrain some latent variables in the neural net with this sensibility that whatever feature it learns should be invariant to some nice analytic transforms. So we're trying to come up with some middle ground like that. Our initial empirical results show that these approaches do blend well with neural net architectures, and they actually do bump up performance a little bit on sufficiently large databases. At least for the time series, we have done that fairly well. We are also beginning to look at TDA approaches, topological data analysis approaches, as a way to impose a broad class of invariances for computer vision problems. And we are very interested in increasing our reach and potential in that area. And I know there's a lot of TDA people in this audience. I'm really keen to connect with them to see how TDA approaches can be positioned as a broad way of achieving practically useful invariances without necessarily choosing a feature up front. And that's where I think some of the sweet spots are. So with that, I will end. Thank you so much. Feel free to send me questions by email. I'll be happy to respond. Thank you so much.